We learned that the standing wave is produced by overlapping two progressive waves that are traveling in opposite direction. So we have here a wave that is progressing to the right. Then this wave can be expressed in this equation, a sine omega t minus kx. Then we overlap it with a reflected wave that is traveling in the opposite direction. Therefore, it's positive kx. Now, if you add these two equations up using the principle of superposition of wave, then this is the equation that we obtain. The amplitude of standing wave cos kx sine omega t. So this is the expression, this is how we obtain the equation for standing wave, and we have derived this equation in an earlier video. So now let's try to understand this equation. Why is there a standing wave, and why is there a cos kx, why is there a sine omega t? So let's plug in some number to replace the amplitude, the omega, and the k over here. So a here is the amplitude of the progressive wave, so you know that it's 1. Omega here depends on the period. Well, I've measured the period, and the period happens to be 1 second. Okay, if you measure it by replaying the video, you get a different value because this is a slow-mo video. Actually, I've already made this video a slow motion video, so but I've measured the time, and the time is 1 second for one complete wave cycle. Therefore, the omega should be 2 pi, whereas the k, as you can see here, one wavelength here is 2 meter. So if it's 2 meter, then we know that our k will be 2 pi divided by 2. Therefore, our k will be pi. So a, the amplitude is 1. Omega, the angular frequency, will be 2 pi. K, the wave number, will be equals to pi. So this is our equation. So this is the equation for y1, this is the equation for y2, and this is the equation for the standing wave that we have for now. As you can see, the amplitude for the standing wave is twice the amplitude of the progressive wave. And the rest, the k and the omega, still remain the same as what we have discussed earlier. So I want to discuss a few things, which is the front part of the equation over here. So we see there's a standing wave, a subscript standing wave over here. So what many people might think is that the a subscript standing wave is representing the amplitude of a standing wave. But that is actually slightly incorrect. Okay, a subscript standing wave over here is actually representing the maximum amplitude of standing wave. Why do we say it's maximum amplitude? Because if you look at different location, let's say you track x equals to 1, you can see that the amplitude is at 2. The amplitude is at 2. Okay, and then you can see that's a very big amplitude. But let's say if you're focusing at point, let's say 1.25, 1.25 is over here. Then if you measure, then the amplitude is somewhere not reaching 2. It's somewhere here. That's your amplitude for 1.25. At x equals to 1.25, you can see that amplitude is somewhere around here. It's definitely less than 2. So at different location, you can get different amplitude. But the maximum amplitude across the whole standing wave, it's in this case 2, and therefore a subscript standing wave here, it's 2. It's the maximum amplitude for this standing wave. Not all position can obtain this maximum amplitude. And as you will learn in the future videos, it's at the antinode that we see that the amplitude is maximum. Okay, so this is a subscript SW. A subscript standing wave is the maximum amplitude of the standing wave. Next, we progress to include the cosine kx at the back. If you look at a standing wave cosine kx, then this term here will be representing the amplitude of the standing wave at position x. That means, right, if you want to find the amplitude, let's say at 1.25 that we mentioned just now, what I can do is just substitute in 1.25 into the x. Then what you get for a subscript standing wave cos kx here, this whole term here will represent the amplitude of the standing wave at this position x equals to 1.25. So let's try to determine the amplitude at different locations along this standing wave over here. So our first example will be taking x is equals to 1.0 meter. So if you look at x equals to 1.0 meter, we can see that the amplitude is at the maximum, which is 2. So let's see whether a standing wave cosine kx will give us 2 or not for its amplitude. So we substitute in 1.0 into to replace the x over here. So cos times pi is just -1. Cos times pi equals to -1. So -1 times 2 is -2 sine omega t. So we can see that this is actually an equation -2 sine 2 pi t. So this is actually an SHM equation actually. It's a x is equals to a sine omega t that you learned in chapter 9. Just that x is now replaced with y because y is where the direction in which we oscillate. Then 2 represents the amplitude of the simple harmonic motion. Negative sign means by it starts at the equilibrium position, goes down first at the start of the time equals to 0. When it starts, then you go by a negative sine curve. Then 2 pi is the omega, the angular frequency of the SHM, and t, the usual one. So let's look at this graph over here. Let's replay it from time equals to 0. Focus at time, focus at time, focus at how the particle at x equals to 1 move when I start the timer. You should be seeing that because it's a negative sign curve, you should see that this particle should start by moving downward first, then upwards, then downwards. It should follow a negative sign pattern. So let's try and look at it. Start. You can see that this particle is definitely moving down, then up, then down. So it's following a negative sign pattern of moving for this particle at x equals to 1.0 meter. So this is the equation here, and because I say this is the amplitude, therefore you know that the amplitude at x is equals to 1 will be 2. Okay, amplitude is a magnitude, so we don't care about the direction. So the amplitude at x is equals to 1.0 meter, it's 2 meter. Okay, next example, we have x is equals to 1.5. So x is equals to 1.5 is over here. So you can see that at this point over here, this point doesn't go up or doesn't go down. It always remains at y equals to 0. So you should expect that the amplitude at this position here should be 0 because it never goes up, it never goes down. The maximum displacement that you can achieve at this position is 0. So if you sub in 1.5 to replace x over here, cos times 3 over 2. 1.5 is 3 over 2 times pi times, then you cosine it, you get 0. So what do you get here? It's just 0 sine 2 pi t. 0 sine 2 pi t, you can read from here that this will be representing the amplitude of the SHM at x is equals to 1.5. So x is equals to a sine omega t. Replace it in chapter 10, it become y is equals to a sine omega t. So the SHM at x is equals to 1.5. The amplitude is equals to 0, just as what we predict earlier. Okay, of course 0 times anything behind you get 0. So that means the displacement is always 0 at x is equals to 1.5 meter. Next, you look at x is equals to 1.75 meter. So 1.75 is around here. So you should expect the amplitude to be somewhere in between. Okay, it's over here, somewhere between 1 and 2. So you should 1 point something maybe. Okay, so if you substitute 1.75 to replace the x over here, you should get, okay, so this is square root of 2 sine 2 pi t. So square root of 2 is definitely somewhere between 1 and 2. Okay, something like 1.4, 1.3, can't remember. Okay, so this tells you that it will have an amplitude at x is equals to 1.75. The amplitude will be somewhere around between, will be at square root of 2, which is around 1.4, I think. Okay, so it's a sine curve, means by when the time starts, it should start by the object moving upwards first. The particle at x is equal to 1.75 will be moving upwards when the time starts. So let's try to see whether that's true or not. So we come back to the start. Oops. We'll come back to the start. Then we play. When we play, right, focus at what happens at x equals to 1.75. If it follows the equation over here, it should be moving upwards first, then downwards, then upwards, because it's a sine. So let's try and see. Start, then focus on the particle. It goes up, then down, then up. So definitely it follows a positive sign kind of oscillation. So what we see here, it's what we predict in the equation here, it's true in the diagram here. Okay, so A subscript standing wave cos x, this portion of the equation here will tells us the amplitude of the standing wave at position x. So at x is equal to 1.0, the amplitude is 2. At x is equal to 1.5, the amplitude is 0. At x is equal to 1.75, the amplitude is square root of 2. So if you are asked to find the amplitude at a certain position, you can just calculate A standing wave cosine kx. But remember, the A subscript standing wave, the amplitude for the standing wave, it's always twice the value of the amplitude of the progressive wave. This one is important. Okay, now another thing I want to emphasize is that the particles between two adjacent nodes vibrate with different amplitudes. So nodes are places where you have no displacement. So 1.5 is a node, 2.5 is a node, 3.5 is a node, 4.5 is a node, 5.5 is a node. At this location, you see zero displacement. So these positions here are nodes. And they say particles between two adjacent nodes vibrate with different amplitude. So that means two adjacent nodes is like 0.5 and 1.5. They are two adjacent nodes. 1.5 and 2.5, they are two adjacent nodes. 2.5 and 3.5, they are adjacent nodes. So if you look at the particles in between two adjacent nodes, you see that they all vibrate with different amplitudes. If you are nearer to the nodes, if you are nearer to 0.5 or you are nearer to 1.5, you will have a smaller amplitude. Okay, but if you are at the center between these two adjacent nodes, so the center of 0.5 and 1.5 is 1.0. If you are at the center of between these two nodes, then you see that the amplitude is maximum. Okay, we call this point as an antinode actually. Okay, so what you need to know is that all the particles in between two adjacent nodes vibrate with different amplitude. They are all vibrating together. They are having a same phase. They reach the peak together, they reach the trough together. They reach the peak together, they reach the trough together. But their peak and trough are at different amplitude. Okay, nearer to the nodes, you should get smaller amplitude. At the center in between the two nodes, you should get maximum amplitude. So that's the characteristics of a standing wave.